may I begin by saying that stack is a very remarkable data structure. So that is one of my favorite data structures, by the way. So that is because of its versatility. So we're going to talk about it a bit further. So one moment. So this is the first part of my talk, of my stack talks. So part 2 will consist of looking of some stack implementations and add some source code for how a stack is implemented using a linked list. Okay. Now let's go on to outline. So let's look at some outline for the stack talks. So here are the topics I will be covering is in this talk as well as the others. So first, we'll answer the question, what is a stack, when and where it is used. Then we'll look at some some really cool examples of some problems where stacks can be used to solve used to solve, including some basic checking, syntax checking in programming languages, for example, some brackets, valid bracket system sequence, and we're also going to look at some more, advanced or complicated examples such as Tower of Hanoi, for example, or some other examples. So afterwards, we'll briefly look at how these stacks are implemented, their time complexity, and these, technical details. And next, we're going to look at the code. Okay, so now let's discuss what is a stack. So a stack is one-ended linear data structure which models a real-world stack by having two primarily operations. So the stacks, in other words, have two primarily operations. The first is push, and the second is pop. So below, on the bottom of the slide, can you see the example at the bottom of the slide?
I can.
Okay, works.
Data, push, pop, top.
Yeah, that's it. So here we have a stack. Let's say I have an image of the stack, and there is some data member getting popped off the stack, getting deleted off the stack, we can say in other words. And one is getting pushed or added to the stack. And also notice that there is a top pointer that...
I don't know if it's deleted. Wait. I don't know if it's deleted. I think it's just, it is... it is when you pop something off the stack, the counter is moved in the stack. But I don't think that item is deleted off the stack necessarily. You have to think about that. Yeah. Okay. Go ahead, though.
Oh, okay.
Go ahead, Bruce.
So
sorry about that.
One moment. Okay. So also notice that there is a top pointer pointing to the block at the top of the stack. So, one moment. So as we know, the stack is one-ended. So the elements in stack always get removed and added to the top of this pile or stack. So that is also commonly known as LIFO. So that is last in, first out. Last in, first out. So let's look at a more detailed example of how we can how things added and removed or pushed and popped from the stack. Okay.
Right.
Okay, now let's look at this. So in this example, we have a list of instructions at the left side, at the left half, so that are about to be performed with our stack. And we have our stack on the right hand side. So let's have a walk through and see what happens. Okay, the first instruction is says pop. So we remove the top element from the stack. So in our case, we're popping apple from the stack. Okay. And next, then we have instruction says to push onion to the stack. So we add onion to the top of our pile or to the top of our stack. Okay, and let's move on to the next instruction. We want now the next instruction, we push celery into the stack, into our stack. So that's pretty simple. And next is watermelon, and we also want to push it. We want to put it on the top of celery, which is now the top of the stack. And now, for example, we want to do pop operation. So the next operation says pop. So we remove the element from the top of the stack. So this is watermelon, which we have just added. Okay. We are removing watermelon now, and so this again. And next instruction also says pop. So we remove the element, and this time from the top, and this time this operation is celery. This time being celery. Okay, we're popping it, and the last operation we want to perform is to push lettuce on the top of the stack. So we add lettuce to the top of our stack. Okay, now we have looked how we can do some operations. So now we understand the basics of what is the stack and how it works. And now let's look where does it get used. So that is maybe surprisingly, but stacks are used almost everywhere. So they are used in text editors, for example, to undo the text you have just written, or in browsers to navigate backwards and forwards by the pages, by the links. So they're used, for example, in some they're used in some compilers or code code writings, some code editors, and to make sure you have written the correct number of matching braces in the right order. So that is the one problem we're going to look now. Okay, problem. So stacks also can be used to model some real-world books, plates, and even games. So one of the example of the game we're going to look at the next part, but that is known as Tower of Hanoi. So that is very well-known problem, and by the way, that is very ancient. And next, stacks are also used behind the scenes to support recursion in some programming languages by keeping track of previous function calls. So when a function returns, it pops the current stack frame of the stack, and rewinds to the next function that called it in the stack. So it's rather remarkable that we use stacks by writing programs, on some programming languages, and we never ever notice it. We didn't know about it even. Something else you can do, for example, you can use these stacks to do some depth research on a graph. So that means that is well-known fact that depth first search can be done in two ways: by maintaining the stack by our own, or using recursion. Well, guess what? Both use stacks, as we have just discussed. So that means that these stacks are versatile and so they're used everywhere, by the way. Now let's look at some complexity analysis. Okay, now the following complexity table that is very important, very important note here, that also only works, that table assumes you implemented a stack using a linked list data structure. So pushing takes constant time because we have a reference to the top of the stack all the time. So we can push new element very, very quickly by just because we have a pointer, we have reference to the top of the stack. Same argument goes for popping. We can remove our pop element from the array or from the stack very, very quickly because we have a reference on the top of the stack. And the same goes for peeking. Okay. Searching, however, still takes a linear time. That might be strange. Why does it takes a linear time? But the element we're searching isn't necessarily at the top of the stack. So in some case, we have to process or look it on the stack by going deeply at the stack. And in the worst case, it might be at the very bottom of the stack, meaning that we have to search all the elements in the stack until we find it. Okay, that is simple. Now, getting the size of the stack is a constant time. That might be strange. Why? So, don't we need, for example, here to look through the stack and making a counter and something like that? Or don't we have to loop every element? No. That is because we're able to maintain some number of elements on the stack. We can do this in this way. When we're pushing element, when a push operation happens, we add 1 to our counter, and if a pop operation happens, we're adding -1 to this counter. This is pretty simple. Okay. Let's look at an example of the stack where the stack can be very useful. Let's look at the problem. So we're given a string made up of the following brackets, and we want to determine whether the brackets properly match. So let's look at some examples. So the first case, they are pretty obvious that they are properly matched. We have a left bracket, square bracket, and a right bracket, and the same one to the other bracket type. And for the next bracket sequence, that is also might be obvious that this is valid because we have these brackets. For every opening, for every left bracket, we have some right bracket, and for the third one, it is very simply that is invalid because we have the right bracket, not the same type, but the other type from the left bracket, and the same one goes for the next example. So by the way, I think these examples are simple. By the way, so does these examples make sense?
They do.
Okay. Hopefully. So now let's look at some example. Let's look at the solution. Okay. So in the first example, let's consider the following bracket sequence. So we and as we are processing the string from left to right, I will be displaying the current bracket to the associated reversed bracket. So for left bracket, for example, we have right bracket, and for right we have left bracket. That's pretty simple. So let's begin. So let's process the first bracket. So that is left bracket, and for every left bracket, let's simply push it to the stack. And so this left square bracket highlighted in blue. So is the slide has changed now? If it is highlighted in blue?
Yeah.
Okay, hopefully. So it works. Okay.
I'm looking at the left bracket right now.
Sorry?
Is that what you want? Right now, you're displaying the leftmost bracket. Is that what you want, or did you want to show the right the right bracket?
The right bracket. What? Can you repeat it, please?
Oh, okay, so you on your slide you show current bracket. It's highlighted.
Yes,
The
yes.
left bracket.
Let's highlight.
Bracket. Okay. Now I don't know about this term reverse bracket. I think we would just call it right. Uh, wait. What would we call these? Yeah, left bracket, right bracket.
Oh, okay. So, we're calling it reverse bracket because, uh, for
Yeah. Okay.
our current bracket,
See,
for example, if we're processing the right bracket at some moment, the reversed bracket will be left bracket. So, for right,
oh, okay, got
so the current bracket that is where we're now uh, processing, and the reverse bracket is the reverse bracket for it. So for left bracket that is right bracket, and for right bracket that is left bracket. So okay, so does that make
it. Okay.
sense?
Okay. Yeah.
Okay, okay. So same goes from for the next left bracket, square bracket. So we again have some. Oh, one moment. So we again have the opening, the left bracket. So can we say here that is opening bracket?
Let me left. Can we say opening bracket? I haven't heard that term. It's possible.
Okay.
Close. You could say open bracket, close bracket. Maybe. Yeah. I think people would understand it. I don't know if it's a technical term. We just say left bracket, right bracket.
Oh, okay, okay, that makes
Honestly.
sense. Thank you.
Yeah, left bracket, right bracket.
Okay.
Yeah. If it faces to the left, it's left bracket. If
Okay.
it faces right,
Okay.
yeah,
Okay.
then
So
it's
uh, now the next is all again. That is the left, some bracket, curly bracket, and for this one we're again pushing it to the stack. Okay, next
okay.
bracket is a right square bracket. So whenever we encounter some, yes, that's not square but curly. So whenever we encounter some right bracket, we need to do two checks. So we need to check two things. The first, if the stack is empty. If so, that means there is no left bracket for a given right bracket, and that means that our bracket sequence is invalid. But if there is so next we can pop some top element from the top element and check if this element we have just popped is equal to the reverse bracket. So that is why we're looking at the reverse bracket. So in this case, let me turn on the. Okay, so if we're checking if this bracket is if the so you do see the pointer now. I have.
I do.
Okay, so we're checking if this bracket at the top of the top of our stack is equal to our
Yeah,
reverse
yeah. Okay.
bracket.
Left curly bracket, current curly bracket. Yeah, you're just a point for you. This okay because you use the word bracket a lot in your talk. It's just a suggestion. Okay, so the curly bracket is also called a brace.
Okay.
BRACE, right? Okay, so they're different. Okay, say a brace is always a curly bone. It's the same as a curly
Okay.
bracket. So if
Thank
you
you.
said, so that way I would know the difference between
Okay.
used bracket, you know,
Okay.
does that make
Yes, that
sense?
makes sense. And is there a word?
Yeah, because otherwise it makes it easier for me to tell what you're talking about.
Okay.
If you talk about the left brace, right brace, then I know it's not the brackets that you just talked about.
Okay. So is there some specific word for some other types of bracket?
Okay, so there is left bracket. I'm sorry, there are brackets, braces, and parentheses. You know what those are, right? Okay, like, oh yeah, you have them in your example. Okay, so in your example, the ones that uh, are roundish or curved,
Okay.
those are parentheses.
Oh,
Those
okay.
are
I got it.
parentheses.
Thank you.
Those are the computer terms that we use for this. So brackets are the square shaped ones. The curly ones are braces, and the roundish ones are parentheses. Those are all computer terms.
Okay. Thank you. Thank you.
No problem.
Okay. So, now we're checking if this bracket, this brace at the top of our stack is equal to the reversed, of our current bracket. So if so, in our case, they are equal to the reversed bracket, so we're good. So we can, so we have popped this element. We're popping this element to check it. So we're popping it, and we're going to the next bracket. So next is a right. Next is a right, some bracket, square bracket. So if this stack is empty, we're checking if the stack is empty. No, okay, that means that is good. So if the top element is equal to the reverse bracket, yes. Okay, we're keep going. So we're popping this one to check. And next is a round left bracket. We're pushing it to the stack. So there, we can call it a left parenthesis. So is there a word? How can we, how can we say parentheses? And
left parenthesis.
Not
right parenthesis.
Not
parenthesis.
How?
Do you want? I could type it.
No. When. How can we? How can we? Is there a word for parentheses in singular or singular form?
Yeah. That's what I'm going to type. Okay, so these are technical terms.
Okay, thank you. Thank you. So, we're now looking where we now have some round parentheses. So let's push it on our stack. And next is a square, is the right parentheses. So we're checking first if the stack is empty. No, in our case it's not empty. So this is good. So if the top element of the stack equal to the reverse bracket, if the top element of this stack, if this value is equal to, if this element is equal to this reverse bracket, yes it is. So we're good. So we're popping this element and going to the next, or another right bracket. So is our stack empty? No. Okay, good. Is the top element of the stack equal to the reverse bracket if this value is equal to this value? Yes. Okay, good. So, alright, so we have now looked at the bracket sequence, we have processed it. So how can we know is it valid or invalid as we have processed it? So once we've done processing the string or the sequence of brackets, we need to make sure the stack is empty. Why? Because well, in this case, if the last few brackets, for example, a few characters in our string were, for example, left braces, then and there would be no right brace for them. For example, they would be still in the stack, and it wouldn't be empty. But if the stack is empty, so we can conclude that our bracket sequence is valid, for example. And in our case, the stack is empty, so we can say that this bracket sequence is valid. Okay, now let's look at another bracket sequence. All right.
Okay.
Let's look at another bracket sequence. Yeah. So the first bracket is a left bracket. So let's push it on the stack. And the second bracket is also a left bracket, and we're again pushing it on the stack. So the next bracket is a right bracket. So let's check is the stack is empty? No. All right. Now let's now is the top element of the stack, if this one is equal to the reversed bracket or the reverse brace in our case? Yes, it is. So we're popping it. And next, the next bracket, the next element we're processing here, the next element we're processing here is a right bracket. So is the stack empty? No. We're good. If the reverse bracket is this value equal to this value? No. So it's not this. So it's not. So that means that our bracket sequence is invalid. Okay.
Right.
So we don't have to process these elements because it is already invalid. Okay. Now let's walk through the pseudocode quickly. So okay. Now let's declare the some s is a stack. So let's loop every bracket in our bracket sequence or in a bracket string. So first we're getting the reversed value from the function. So we're going to write this function a bit further. So and then we're checking if our bracket is equal to the left bracket. If so, we're pushing it. But else, if our stack is empty, or if our stack, if the value you have just popped isn't equal to the reverse value, that means that our bracket sequence is invalid, and we're returning false. Otherwise, and once we have done the our loop, we're returning we're returning the Boolean value. So if our stack is empty, we're returning true, and otherwise we're returning false. Okay. So this method is doing this problem. Okay, well that's it. That's it for today. I'll turn the demonstration off. Okay.
I have a question.
So that's it for today. That's it for my talk for today.
Okay.
So.
Quick question. Wait. Quick question. Okay. In your talk, did you say that stacks are linked lists?
Sorry.
Or no? In your talk, did you say that stacks are linked lists?
Oh, so I said that stacks are implemented in some program languages. So as I know, I have a code on Java. So in Java, these are implemented using a linked list. They're implementing using a linked list.
Okay. In Java, they're implemented. Okay, but they don't have to be.
They don't have to be. Yeah.
They could be just.
Yeah.
No. Okay. I just want to be clear because because when I looked at the order of you, okay, so you gave the order of complexity for a push or pop, right? In a static stack, that's correct, right? It's order 1 because you're just moving your pointer in your array or your structure, right? You're moving it up and down, right? But if you're pushing something in a linked list, it's not order 1, I don't think, is it?
Well,
okay,
yes.
It is. Okay, maybe. Well, yeah, then I'm wrong. Okay, I thought it took more time. Okay, but I know, like you. Okay, if it's a fixed data structure, right, like a static data structure, then you could just move the pointer in that structure up and down, and so there's no. It is order 1. That I know.
Okay. So, okay.
But I don't know for a linked list, okay? Because linked list, you're
okay. So when
it takes time to move through a linked list. It takes time.